So hello year 12, or should I say year 13 now, because of course we are starting your A-level material, A2 as was. And I'm so delighted that I actually get to do this topic for once, because this is what I really enjoy. So we're going to start by looking at 13B, topic 13B, appropriate now that you're year 13, and it's all about entropy, moving on to free energy, and whether or not reactions go, and if so, how far. But I think this really is proper chemistry, finally, that we're getting our teeth into. And just to show you why it's so important to me, my first ever paper was this one. Folding of a Lysem domain, entropy, enthalpy compensation in the transition state of an ideal two-state folder. If you're really bored, you're welcome to have a look at it. But just to say that this stuff is what I really enjoy. This is the spec for topic 13B, entropy. I won't bother you with all of it, but I'm just going to say today we're going to focus on the first three sections. Understand that since some endothermic reactions can occur at room temperature, enthalpy changes alone do not control whether reactions occur. Know that entropy is a measure of the disorder of a system, and that the natural direction of change is increasing total entropy, positive entropy, and understand why entropy changes occur in particular examples. And I draw your attention to the fact here that the exam board actually even specifies a series of reactions that you need to be able to be familiar with and be able to discuss in terms of entropy changes. Essentially, the whole topic here is about what determines whether a chemical reaction will go or not. Can it occur? Will it occur? And if it will occur, how far will it go? Will it go completely to products, some way to products, or will it only go a little way? So pause the video and have a think about reactions that are spontaneous and reactions that aren't. That is, reactions that will just go by themselves. Maybe they need an ignition to get them going, but once going they will run by themselves. And then see if you can come up with any reactions that will not go unless you are constantly putting in energy. Okay, reactions that go. There are some very obvious ones here. Combustion is the most obvious one. Yeah, you need a spark, but once it's going, that forest fire will just rage for days or weeks or even months without actually needing any more energy input. It is self-sustaining. You put potassium into water, it doesn't even need a spark, it just goes, it reacts. Burning magnesium, again we need to get it hot, but once it's ignited it will continue to burn, so that is an oxidation reaction. Rusting, much slower than the first three examples, but we don't need to put in any energy for iron to rust. It does that naturally without any help. Glow sticks, once those chemicals are mixed, once you've snapped the glow stick, that will continue to glow. And batteries, once you connect them up in a circuit, that chemical reaction will run, producing energy and running your iPhone or your torch or whatever it is. Reactions that don't go, well, things like the Haber process. As you know from your GCSE, you need to put in a lot of energy to make that go. Electrolysis of aluminium oxide, sucking up about 5 to 10% of the UK's electricity. Constant energy input to make that reaction go. That is not spontaneous. If there's a power cut, the reaction stops instantly. Photosynthesis, it needs constant light put in to make it go. If the cloud goes, if the sun goes behind a cloud, the reaction slows. At night time, the reaction stops. It is not self-sustaining. It does not continue without input. And of course, thermal decomposition, heating up your carbonates, which you did in the Group 2 project, and the nitrates, which you did in the Group 2 project. If you stop heating them, they stop decomposing. The reaction does not continue in the absence of energy being supplied. So these on the left, these are reactions that go, they are spontaneous. These are reactions that don't go, they are non-spontaneous. A spontaneous reaction is a reaction that favours the formation of products at the conditions under which the reaction is occurring. It occurs without the addition of external energy. It may need some energy to start it off, but actually once that's going, it will continue without the addition of external energy, and it favours the formation of products. So looking at those two groups, can you work out the difference between spontaneous reactions and non-spontaneous reactions? Well, I reckon by now you're probably thinking along these lines. Hey, exothermic reactions are spontaneous and form products with no energy input. So we had combustion releasing heat, we had fuel cells releasing electricity, we had glow sticks releasing light, oxidation. Hey, these are exothermic reactions, they continue by themselves. Endothermic reactions though, they're not spontaneous. We need to put in energy continually to form products like photosynthesis for light energy, electrolysis, electrical energy, thermal decomposition, heat energy. So you might be thinking exothermic reactions are spontaneous, endothermic reactions not spontaneous. And that's because that's generally true, but it's not exclusively true. There are reactions that break this rule. So here's the first.
What I have is some barium hydroxide. Okay, and I'm going to put this into the... In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
What's with the hand stuff?
What hand stuff?
The hand sanitizer gel.
Oh, it just lives on my desk.
Oh.
I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second.
Oh, sweet.
So, I'm going to mix these two things together and carefully... I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk, you wouldn't want to put it in coffee. Okay, if you put that in coffee, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I've just breathed the who's load in. That sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the best one you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom.
How
And
cold
that is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So
Freezes at 10.
this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to melt. In fact, there's actually ice crystals forming on the side of there.
Can I touch the side? It's
cool.
so cool.
Yeah. No. Sorry.
So, there you have it. A reaction that spontaneously goes but yet sucks in energy from the environment. An endothermic reaction that is spontaneous. And if you want to do one at home, then you can have a go at this. So again, a reaction that spontaneously goes but is endothermic. There, you're adding salt to the ice and the salt dissolving in the water there when the ice is melting actually is an endothermic process, takes in energy. So clearly some endothermic processes are spontaneous. So there's more to it than just the enthalpy change. So most exothermic reactions are spontaneous and will form products without an energy input. Just to remind you, because we are building on your year 12 material, an exothermic reaction is one where the products have less energy than the reactants. Remember H, enthalpy here, bond energies, and because the products have less energy than the reactants, that extra energy is given out, usually as heat to the surroundings. We would say delta H is negative. The change from reactants to products is negative. And remember, A-level, the arrow is really important. You need the arrow going in the right direction, and you need to be very careful with the fact that the arrow is showing the right energy change. Most endothermic reactions are not spontaneous and only form products with an energy input. So here we go again. The products have more enthalpy, H, more bond energy than the reactants. And that means some extra energy has come in. So perhaps heat energy, perhaps light, perhaps electricity, but energy has been supplied, and the bond enthalpy, delta H, is positive. So the arrow going up for these reactions. But some of these reactions, some endothermic reactions, are spontaneous. So clearly there is more to it than just the enthalpy change of the reaction. It is useful to borrow an analogy from GCSE physics, which I know all of you have done. Some of you have lost it and dropped it very happily more than a year ago now. But if we think about how much energy the apple has here, well, I can look at this picture and I can say, well, from this picture, I can sense that it's about 1.5 metre off the ground. I know that the apple is about 100 grams, which is 0.1 kilograms. And so for I can estimate it by E is equals mgh, which is approximately 0.1 times 10 times by 1.5. And I can get the energy in terms of the number of joules, 1.5 joules. Okay, from the picture we can work out it's about 150 centimetres off the ground. If you want to be more precise, 1.47 joules of gravitational potential energy. But there are other forms of energy that are not obvious from this picture. And you might be thinking of chemical energy. The apple contains chemical energy that is less obvious from this picture. The apple also contains kinetic energy. We can't tell from this picture how fast the apple is moving. We can probably work it out if we can estimate where it fell from and use our Suvat equations for the physicists among you. But there's hidden energy, energy that we haven't considered by just looking at that static picture. In a similar way, when we do our bond energy calculations, for example here, the combustion of methane and oxygen forming water and carbon dioxide, we can tot up the bond dissociation energies of the reactants and we'll get 2,648 kilojoules per mole. We can tot up the bond energies of the products and we would get 3,466 kilojoules per mole. Reactants minus products, total energy change, and I'm going to say total enthalpy change, is minus 818 kilojoules per mole. But there is another form of energy that we are neglecting when we just think about enthalpy. We're only considering the energy of the chemical bonds when we do this. There is another form of energy that is missing from our calculation, and that is entropy. So entropy, it's not quite an energy, but I'm not going to make that distinction now. I will come back to that in a couple of lessons' time and discuss why it's not quite an energy. But entropy is a form of energy that is missing from our consideration. Some photos of my kids' bedrooms. Does your room look anything like this? If so, you already know about entropy, because what entropy is it measures the amount of disorder in the system. A more disordered system has high entropy, a less disordered system has low entropy. So here, this is very ordered. This is low entropy. Over here, this is very disordered. And we would say that this was high entropy. So let's have an example. Here we've got a 40 by 40 grid, 1,600 squares. If we have 100 of those squares at any one point being red. This is one particular arrangement of the red squares. So which arrangement, if you randomly coloured 100 squares red, what's more likely to occur? This arrangement or this arrangement? The important thing is the number of possible arrangements. That determines the entropy of a system. There is only one way you can colour 100 squares red and have them in a box at the centre. There's only one way of doing that. That therefore is a very ordered system, and it is very low entropy. So very ordered, very low entropy. In terms of the face, now there's only one way to colour 100 squares to make that face. But the fact is, are you really going to be able to distinguish all those faces from each other? No, you won't. Is that the same face that we had previously? No, it's not. If you go back and we look at the nose here, the difference between those two is that the nose has moved. So although each face, each absolute face, there's only one way of doing it, there are hundreds of arrangements that look like a face. They're all slightly different. Each face, there's only one way of doing it. But if you said, oh, I can see a face in my squares, there are hundreds of arrangements that you would class as a face. And so a face is much more probable than that one way of having a square in the centre. So square in the centre one way, a face hundreds of ways. All slightly different, but they're all a face. There's only one way of colouring in the squares exactly like this. However, to most of us, or to all of us I would suggest, this is a random arrangement. And we would not be able to instantly distinguish one random arrangement of squares from another. And out of the 10 to the 162 possible arrangements, most of them look random like this. And if we group them all together as random, then we would say that random is overwhelmingly more probable than a face or a box. So if your screen flashed up arrangements at random 1 a second for your entire lifetime, you would only ever see random arrangements. You would never, in your entire lifetime, see a face. You would certainly never see that one square. If everybody in the world sat and watched these 1 a second for their entire lives, probably no one in the world would ever see that square. because it's just so unlikely to occur randomly. Only one arrangement out of 10 to the 162. Some more examples. How many shakes of a tube of Smarties would you need to do to get all the colours to line up? It is possible that if you shook a tube of Smarties endlessly, you would end up with all the greens on one side, all the blues on the other, the pinks in the middle, the browns, the yellows. But it's never going to happen in reality because it's so unlikely. Another example, theoretically, you could shuffle a random pack of cards and get them completely back in the order that they started in. Ace of spades, all the way through to the king of spades, then diamonds, clubs, hearts. It's possible. There is a way that that could occur randomly. But the chance of that happening is 52 times 51 times 50 times 50 all the way down to 2 times 1, which is something called 52 factorial for the mathematicians among you. And that is 80,700 billion, 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 billion combinations, and you would require one to be right. I mean, if you were shuffling from the start of the universe for 14.5 billion years ago, you still would not have got that arrangement back. It's just so improbable. It can happen, it just won't. In a spontaneous process, the direction of change is always from a more ordered, less probable state to a more disordered, more probable state. So the universe just does this. So if you've got a tube of Smarties and you've got a load of green Smarties on one side and red Smarties on the other side, and you shake them, then you're going to end up with a mixture where the greens and the reds are all mixed together. And that is because disordered states are just far more likely to exist or emerge than ordered states. And what you need to be able to do is discuss whether or not you think a chemical reaction is becoming more ordered or more disordered. So entropy is a measure of disorder. A pile of books stacked up neatly is not very likely is ordered. More likely your bedroom, your books look like the cartoon on the right. As the disorder within the system increases, its entropy increases. It is more likely that stuff is randomly distributed around the room rather than in neat piles, and my desk certainly will attest to that. We can put some maths on it. Now, we're going slightly beyond the A-level spec here, so this is not something that you have to learn. So I'm going to say beyond A-level spec. But it is useful to understand where this is coming from. This guy Ludwig Boltzmann, the Boltzmann constant, you've probably used that in your kinetics lessons. If not, you certainly will be using that in your kinetics lessons by the end of the year. It's related very strongly to the ideal gas constant, R. So that K is related to R. His greatest achievement was this. The entropy of a system is a constant, Boltzmann's constant, times the logarithm of the ways of arranging that system. Some of you won't be familiar with logs yet, but you certainly need to use those in year 13. They will come in many courses. So the logarithm of the ways of arranging stuff. And because the ways of arranging stuff is always a positive number, log W is always a positive number. That is a constant. So the entropy of a system is always a positive number. The only exception to that is or 0. But the entropy of a system is always a positive number. It always has some disorder. So how does the number of students affect the entropy? Well, imagine if I've got 32 desks in my classroom and there are no students in it at all. There's only one way of arranging that, and that is to have 32 empty desks. So S would be K times log 1. Log of 1 is 0, so that has no entropy. So the only way to have no entropy is if you have no chemical or no energy. Then you'll have 0 entropy. Other than that, there is going to be some entropy. Let's say I just have one student. Well, she has a choice of the 32 desks in the classroom. 32 desks, one student, 32 possible arrangements. I'm not putting the constant in because it's such a small number, but the entropy is 1.5 units of entropy. Okay. What about 2 students? Well, the first student has 32 options for where to sit. The second student has 31 options for where to sit. 32 desks, 2 students. Now, because the students are identical, as 2 molecules of a chemical would be, or 2 quanta of energy would be, I can't tell the difference between them. So it doesn't matter to me whether student A is sitting there and student B is sitting there, or B and A, they look the same. So actually, the maths that we would do is 32 times 31 divided by 2, which gives us the 496 possible arrangements. Again, I say this is beyond A level, but it might be useful for you to actually just follow what I'm doing. So there's 496 possible arrangements. And therefore, when I put the maths in, log 496, the entropy is now about 2.7 units. It's about double, just under slightly double, almost twice as much entropy as 1 student. With 3 students, 32 desks, the first one has 32 options, the second one has 31 options, the third one has 30 options. But I can't tell the difference between A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. So for every combination of 3 students, there are 6 identical ones. So I divide by 6, 3 times 2 times 1. And that gives me 4,960 possible arrangements. And if I plug that in, I get 3.7 units of entropy. And finally, with 4 students, 32 desks, 4 students, 35,960 possible arrangements. If you're interested in following the maths, you don't need to remember 32 times 31 times 30 times 29, but I can't tell the difference between those students, so I need to divide by 4 times 3 times 2 times 1, and that gives me 35,960 possible arrangements, or an entropy of 4.6 units. Okay, you don't need to know that, but the next slide is what you all need to know. More chemical means more entropy. And because the number of positions available to an atom is immeasurably huge, it is true that twice as many moles means twice the entropy. It wasn't quite true with the calculations I just did, and that's because there were a limited number of ways of arranging the students. But if you've got an almost unlimited space, then it will be absolutely true that if you've got twice the chemical, you've got twice the entropy, 4 times the moles, 4 times the entropy. There's other things we have to consider rather than just how much we have. Let's imagine the students, you guys sitting in a classroom. How disordered are you? Well, you're all sat at desks. You're in fixed positions. You're not moving about. Yeah, you can wriggle a bit, and you do wriggle a bit. But unless you're particularly brazen, you are all facing the front, facing the teacher, not turning around. So there's actually not that many options for you guys. You sit there at your desk facing forwards, not moving. Low disorder, low entropy. During a practical, you've got more options. There's more positions for you to arrange yourselves around the classroom. The students can rotate around. You don't just have to face the front anymore. You can turn. You can wriggle more. You can step from side to side. So even if you're not turning and moving around the classroom, you can shuffle on your feet a little bit more. There are far more ways of arranging the students in that classroom. It's more disordered, so it's higher entropy. And at lunchtime, when I send you guys out to do whatever it is you do, you have a huge array of places to go. You have the whole school, you've got the field, you can be in almost any positions. Totally free rotation, we don't care which direction you're facing. You can dance, do whatever it is you want. This guy's clearly having fun. Total free vibration. There's a huge number of ways of arranging you guys. It's a very high disorder, and therefore it's a very high entropy situation. Thinking about entropy changes, when you guys get up from your desks to do a practical, entropy is increasing. And when you come in from lunchtime and you sit down at your desks, your entropy is decreasing. This is a spontaneous process. This takes a lot of effort and energy, and I think you'll agree with that. You leap out of your desks to do a practical. With reluctance, you come in and sit down and start learning. And we can apply exactly these ideas to chemicals. So let's look at ice here. The molecules of water are in fixed positions. They can't move. They can vibrate a little bit, and this is showing some of those various vibration and modes that they can do, but they're pretty much stuck in position. They certainly can't rotate. They're held in a fixed orientation. And so there's a very limited number of options available to the molecules, and so it is low entropy. Molecules in water, they can move around, there's more positions available, they can go almost anywhere as long as there's not another water molecule, they can rotate freely, they can vibrate a lot, they're not restricted so much. There's far more ways of arranging those molecules, and there's far more disorder, much higher entropy. Steam, well, water molecules can move anywhere. Completely free rotation, completely free vibration, huge number of ways of arranging those molecules, so there's a high degree of disorder and it's very high entropy. So I think you'll agree, solid ice going to liquid water would involve an increase in entropy, while steam turning straight into ice would be a huge loss in entropy. And the numbers bear this out. The standard entropy of water, right, again, we're using this symbol, S standard. That means at 1 bar pressure and a stated temperature. Remember, you need to know all these definitions from the Year 12 course, Topic 8. We can see that the standard entropy of water is 48 joules per mole per Kelvin. Standard entropy of liquid water is 70 joules per mole per Kelvin. And the standard entropy of steam is 189 joules per mole per Kelvin. Notice the unit, that's not important yet. It's almost joules per mole, but it's not quite. And it's not quite an energy, but we'll come back to that. It is important we are comparing the same things under the same conditions. So all of these entropies are given at 298 Kelvin. You might be asking whether that's possible. Yes, it is possible to have solid water, solid water at 298 Kelvin. And steam at 298 Kelvin. It's just not the most stable state. But these are entropies measured at those, all at room temperature. Steam, water, ice. Lowest order, more disorder, highest entropy. So we need to think here a little bit about the energy levels that electrons can inhabit in the same way that you've seen in the Group 2 course, that electrons can gain energy and jump to a higher energy state, and then they can lose energy and move to a lower energy state. The electrons can only exist in very specific energy levels. Well, it turns out, quantum mechanically, vibration and rotation and translation are all exactly the same. So a particular molecule can't have any vibration. It can only vibrate at set frequencies. So here we had a molecule that was vibrating slowly. If it absorbs infrared radiation, that can move it to a higher energy vibrational state. It can absorb a quantum of energy, a photon of energy, and move to a faster, higher vibrational state. But it cannot exist in the middle. It can only vibrate at set energy levels, just like the electrons can only live at set energy levels. And exactly the same is true of rotation. So here we've got a molecule that is rotating slowly. If it absorbs a photon of microwave energy, it can jump to a higher rotational energy level. It cannot exist in the middle. There is no intermediate rotational level. It can only rotate at set frequencies. And translational energy levels is how fast they're moving in what direction. So some of these molecules are rotating, some of these molecules are vibrating, some of these molecules are moving. All of these have absorbed some energy. All of these can emit some energy to jump between rotational states, vibrational states, and translational states. And as a result, there is a certain way that you can arrange the energy between these. For example, this one that is rotating fast could release some energy and transfer energy across to this one that is, vibrating fast, could release some energy to this one that's vibrating slowly. This one that is rotating rapidly could release some energy and transfer it across to this one that is rotating slowly. And therefore the energy can be arranged in various different ways amongst all the molecules. When you heat up a solid, there's more energy to share between the particles. In a solid, of course, the particles can't rotate, they can't translate, but they can still vibrate. So because in a solid, and we can see in the diagram here, because in a solid the particles can vibrate, we can put the energy amongst those various different vibrational modes and give the system some disorder. The more energy there is, the more options each particle has to vibrate, the more ways of arranging the energy, so more disorder and hence more entropy. If we're talking about a liquid or gas, now these can rotate, these can vibrate, these can translate. Again, if there's more energy, there's more options for vibration, more options for rotation, more options for translation, more disorder, and hence more entropy. So when you heat something up and you give it more energy, there's more ways of distributing that energy amongst the particles, and so there's more disorder, even without a state change. So let's have a look at a graph of entropy against temperature. First thing to notice is at absolute zero, there's no entropy. If you have no energy, there's no vibration, no rotation, no translation, everything is absolutely in a fixed position and not moving. No disorder. Only one way of arranging it, like those 32 students on 32 desks, or no students on 32 desks, and therefore you have no entropy. As you start to provide energy, so as it heats up and there's more energy, there's more ways of vibrating. That energy can be distributed differently, more and more. The more energy you have, the more distribution you have, so you have higher entropy. Until you get to a particular point, the melting point, and then there's suddenly a huge jump in entropy. Why? Because suddenly the particles can rotate, which they couldn't do before, and they can translocate or translate. They can move. And this gives them many more options for how to arrange themselves. As you heat up the liquid, more energy, more options for vibration, rotation, translocation, so the energy increases, the entropy increases again. Until you get here, and look, this is an even bigger jump. Because suddenly the particles are not just contained in a small container, they are free to move anywhere. So they've got a huge number more options available to them. And then again, as you heat up the gas, there's more options for how to distribute all that energy, so there is more disorder. Okay. And I've just stated there, unlike enthalpy, remember we said that there isn't really a zero H. We can only really measure enthalpy relative to isolated atoms. There's not really a zero enthalpy, but there is a zero entropy. This is an absolute zero when there's no energy to share and only one way of arranging the particles. So, estimating entropy changes. Since gases occupy so much space, there are a huge number of ways of arranging the gas particles. Liquids are far more restricted, far fewer ways of arranging the particles. Solids have very little flexibility, no rotation, no movement, no translation, so there are not many different ways of arranging the particles. That means the entropy of a gas is bigger than the entropy of a liquid, which is bigger than the entropy of a solid. If you heat up a solid, liquid or gas without changing state, there's more energy to share, more options for vibration, rotation, translation, more disorder, higher entropy. And finally, if you have more of a chemical, there are more ways of arranging the particles and so higher entropy. Just some general principles for you to learn. Here's an example of a reaction. 4 gas molecules floating about. They react together to form one gas molecule. Does the entropy change? Yes, of course it does. 4 gas molecules become one gas molecule. There are far fewer ways of arranging one gas molecule than arranging 4 gas molecules, so there's a massive entropy decrease in this particular reaction. How about this? This is a thermal decomposition, something like calcium carbonate. You heat it up and you release carbon dioxide. Does the entropy change in this particular example? Yeah, of course it does, because you've got a solid releasing a gas. Since the gas is very, very disordered and the solid is very, very ordered, you are generating a huge amount of disorder from something that was quite ordered to start with, or very ordered to start with, and therefore there's a huge increase in entropy in this system. If you compare helium to xenon, which has a higher entropy, and why? Well, hopefully you considered the particles in there. You realised that helium was much smaller, had fewer electrons, protons, neutrons. That meant that there were far fewer ways of distributing those particles. The electrons, far fewer options for exactly where they were going to be. So it has a lower entropy compared to xenon, which has far more protons, neutrons and electrons. And the electrons in particular, there's a wide variety of ways you can distribute those electrons around the molecule. Which has the higher entropy? Solid sodium chloride or sodium chloride solution? Again, hopefully you realised that in solution the ions are free to move around. They've got far more disorder compared to the regular arrangement in the ionic crystal lattice, and therefore the entropy of solution is much bigger than the entropy of the solid. And how about this reaction? This is the reverse of the Haber process. You're taking two ammonia molecules, you're generating nitrogen gas and hydrogen gas. Well, hopefully you realise in this case there is a big increase in entropy. There's 4 gas molecules or 4 moles of gas floating around, which has far more entropy than 2 moles of gas, and therefore the right hand side has much higher entropy. So, something for you to think about: which has the higher entropy, argon or neon, octane or pentane, bromine gas or bromine liquid? It says use your data booklet to check your answers. Don't worry about that. Have a think. Okay. Hopefully you realise that argon has a higher entropy because argon has a higher relative atomic mass, more electrons, more ways of distributing them, ditto neutrons and protons. Octane has a higher entropy than pentane because octane has a higher relative formula mass, and therefore more electrons, more ways to distribute them, more bending modes, more rotational options as well. And hopefully you realise that bromine gas had a higher entropy than bromine liquid, as gases have higher entropies than liquids. Gases have more energy, higher disorder. So let's have a look at some exam questions related to this. Complete the table by giving the sign of the entropy change of the system for each reaction. Carbon dioxide solid going to carbon dioxide gas. That gets less ordered, and so the sign of the entropy change is positive, increase in entropy. Sodium chloride solid and water forming sodium chloride solution, that gets less ordered, and so the sign of the entropy positive, more entropy, more disorder. This is the Haber process. Nitrogen and 3 hydrogens becoming 2 ammonia molecules. Well, that becomes more ordered. 4 moles of gas become 2 moles of gas, so that has a negative entropy. Now over to you. Pause the video, see if you can predict the entropy change for the following changes. Positive, negative, or about 0. Off you go. Okay, well, liquid to gas, that is going to have a positive change in entropy, more disorder. Solid in a gas becoming a solid, we are losing a huge amount of disorder in this gas. As the copper oxidizes, that is going to lose entropy. 2 ions floating around the solution, lots of options available to them. Solid silver bromide, very ordered, that is going to lose entropy. 2 gas molecules becoming 2 gas molecules, they're all about the same size. There's not going to be much of a change there, so the entropy change is going to be about 0. Methane and oxygen forming carbon dioxide and water, you're going from 3 gas molecules down to just 1 gas molecule. That's a huge loss of entropy, minus. Finally, you've got a free ion and a solid atom, becoming a solid atom and a free ion. Not much of a difference in entropy there, so that's going to be about 0. And there, my answers are clearly wrong. That's clearly negative, losing entropy. I'm going to leave these for you to have a think about, if you wish. 54, identify the process expected to have a delta S value closer to 0. Which processes have an associated increase in entropy? What's the best description of the entropy and enthalpy changes accompanying the sublimation of iodine? Which has the largest increase in entropy? And predict the entropy changes, positive, negative, or about 0 for those reactions. Have a think about those. If you're not sure, get back to me. Right, what I would like you to do in preparation for the next lesson on my half of the course is have a look at this sheet, have a think about the practicals. These are practicals that you would have done in the lessons if school was running normally. And as it says here, you need to be able to discuss these experiments, okay? So for each experiment, what do you think's happened to the enthalpy of the system? That's the chemicals themselves. What's happened to the entropy of the system? This is what we've just looked at. You will need to identify, or if you can't identify, look up the balanced chemical equation to answer that fully. You of course need state symbols. What has happened to the temperature of the surroundings in each case? What do you think has happened to the entropy of the surroundings? So you can come up with an answer for that. Finally, was the reaction spontaneous? Reactions that are slow at room temperature but are helped by a catalyst or kick-started by heating can be classified as spontaneous. Reactions which only go when kept at high temperature should be classified as non-spontaneous. So if you start them and they keep going, they're spontaneous. But if you have to keep supplying energy, they're non-spontaneous. Before next lesson, can you find a rule that separates spontaneous and non-spontaneous reactions? You've got seven of these, 7 videos to watch. You don't necessarily need to write anything. Just have a think about those questions. This should take you about half an hour. This is half of your homework for this week, but it would be beneficial for you to do this before the second lesson later in the week, where you will be getting another half hour of homework. Okay? Until later, do email me if you've got any problems. Otherwise, have a nice week.